Hello and welcome to Some Assembly Required, the CompuSAR project, where we're implementing 70s and 80s computers on FPGAs. In particular, we're starting with implementing the CPU, the 6502, maybe aimed at the more modern version by Western Design Center. Before I get to this video's main subject, I'd like to spend a few minutes talking about how we structure logic arrays in modern design. In modern design, we generally divide the logic into two parts. The first are called asynchronous circuitry. These are traditional logic gates, such as AND, OR, XOR, etc. Maybe not here and there. The thing about them is that they respond to the input as it changes. So when the input changes, the output changes. Between those segments of asynchronous circuitry, we place something called flip-flops. These have data input and clock, and will, upon an edge of a clock, so rising edge or falling edge, will copy the input to the output. And once the output is latched, it does not change until the next clock edge that triggers the flip-flop. Which means that any logic we place here will start responding only when the clock shifts, and then will not change until the next clock. Now, this logic may loop back under certain circumstances, but inside the same asynchronous logic, we do not allow any loops. So we do not allow something like this. Now, if you look at this design, what you would take from it is that we need to figure out how much time we need here. Here's the thing. Whenever the voltage changes on the input from logical 0 to logical 1, it takes time for this to be reflected on the gate's output. This actually shifts electrons around inside, and while electrons have very small mass, that number is not actually 0, which means that we actually need time to let the electrons settle in their new position. So when the input changes, the outside input changes, it takes some time for the asynchronous circuitry to respond to those inputs. And we need the clock to arrive after that time has passed. Because if it arrives before that, we're going to latch the wrong value. Which means that whenever we design a circuit, that circuit has certain timing characteristics. We need to make sure that our design lives up to the timing characteristics we need this circuit to hold. So how do we do that? There are three timings that we can talk about here. The first is the clock. We need the clock to be long enough for that. So if we have a certain logic gate here, and then another flip-flop, we need the clock to be far enough apart that the data here will have time to propagate through all the asynchronous circuitry here before the next clock latches it here. So whatever circuitry we put between the flip-flops determines how rapid the clock we can give the circuit. So that's one timing characteristic, the clock. Another timing characteristic we need to talk about is called the setup time. Even if it takes us, for example, 1 nanosecond for all the circuitry here to settle, if the clock arrives after exactly 1 nanosecond, that's not enough time. The flip-flop might need some time for the data to be steady and holding before the clock for it to latch the value correctly. We call that the setup time. Likewise, it is possible that the flip-flop will remain sensitive to changes sometime after the clock. So we might need this value to hold even after the clock has passed. And we'd call that the hold time. So setup time, hold time, and clock duration. These are the main three timing characteristics of our circuit. How do we make sure our circuit performs well? The first thing to minimize our setup time from the outside is to make sure that all outside inputs see a flip-flop as soon as we can. So we want the minimal amount of time between the input going into our circuitry and a flip-flop latching the value. It's also good for something else called metastability, but I won't discuss that now, possibly in a future video. Something else which isn't as critical, but still makes things simpler, is having a latch on the output. So if we have an output line here, if it connects directly to a latch, we can pretty much guarantee at that point that it will hold steady throughout the clock cycle. However, if we start putting asynchronous logic here, then it will take some time between the clock and the output becoming valid. And that again is something that might hurt us. It seems that the simplest thing to do is make sure all inputs immediately go into a flip-flop and all outputs go into flip-flop immediately before leaving our design. In fact, if we look at the original 6502 design, we see that the design, at least the design we have, had pretty much the same idea. The data goes here and immediately gets latched on this data latch DL register. This data latch can output both to the high order and the low order bytes of the address line, and those feed into another register, which then gets output. And we see that both the data latch and the registers, this is the address bus low, which is the least significant byte, both have a load control, which means exactly what we just said. We have a latch on the input and we have latches on the outputs. So great, we have the right idea. This is the 6502 timing diagram. It's a bit overwhelming, and truthfully, there are better timing diagrams for other chips, but that's what we have, so let's try and handle this one. Let's try and understand how this one is built. First of all, we have labeled arrows. To understand what those means, let's look up a few. So TPWL. TPWL is clock pulse width low. Likewise, TPWH, clock pulse width high. Now, it seems pretty obvious that pulse width low is between the middle of the falling edge and the middle of the rising edge. And likewise, TPWH, pulse width high, is between the middle of the rising edge and the middle of the next falling edge. So it seems pretty obvious that the label here is between the two lines for which it refers. Except that's not true of everything. To understand why, let's look at TF, which is fall time and rise time. Obviously, fall time is between this line and this line. What we understand then is that if the label is between two long lines, then that means it is inside the time period it is labeling. However, if it is just one part with an arrow, it is outside. So TF is between this line and the next one, which is this line. And likewise, TR, the rising time, is between this line and this line. So with that in mind, let's try and start having a look at the timing diagram. Now, the timing diagram is a contract. It tells us what we commit to, what the manufacturer promises will happen. The first thing we need to ask is who is bound by that contract? And the way to answer this question is to look at the pins for which the contract applies. So phi2 is an input pin, so we pretty much assume that this is something that our clock needs to abide by, which means that the CPU is allowed to assume that the fall time is no more than 5 nanoseconds, and that the pulse width low is, we'll assume 14 megahertz, no less than 35 nanoseconds, which means that the CPU has 35 nanoseconds to handle the low area of the clock, and then 35 nanoseconds to handle the high area of the clock, 70 nanoseconds altogether, which are more or less 14 megahertz. Next, we look at A0 through A15, memory lock, read-write, sync, and vector pool. All of those are output pins. So we can assume that this line talks about a contract that the CPU promises to keep. Now let's look at what this contract actually is. We have the address, memory lock, sync, etc. lines, the address part of the bus. And it starts with a falling edge, but it continues from before. And this is corroborated by TAH, which is address hold time, which means that for at least 10 nanoseconds after the falling edge of the clock, the CPU commits to keeping the old address bus valid. And then we have TADS, which is address setup time. The CPU promises that it will take it up to 30 nanoseconds from the falling edge of the clock until the address is set up. Now, this isn't exactly documented here, but we have this gap between the address hold time, which is at least 10 nanoseconds, and the address setup time, which is at most 30 nanoseconds. So we have anywhere between 20 nanoseconds and 0, a time where essentially the address bus is invalid. Now, most timing diagrams actually document it. This one doesn't, so we'll just add this documentation ourselves. We'll mark this area as invalid, and this way we won't get confused about what's going on here. So the address bus is valid after at most 30 nanoseconds after the falling edge of the clock. And then we have TACC. TACC, access time. The access time is the time between the address bus, you see how this line goes up, the address bus being valid, and you will see how this line goes down, the read data being valid. We can see that that's the case because we have TDSR, which is data read setup time, which is a minimum of 10 nanoseconds. So at least 10 nanoseconds before the next falling edge of the clock, this data is valid. It is also valid from the previous part, TDHR, which is data read hold time, again, at least 10 nanoseconds. So it is valid at least 10 nanoseconds after the clock. And in between, guess what? The data is invalid. So again, Western Design Center did not think it was worth it to document that fact, but we'll add this documentation now, and this way it won't confuse us later. So data hold, data invalid, data setup, and data hold again, and so on and so forth. Whose contract is this? Since we're reading data, the data must be supplied by the external memory. So this contract, at least 10 nanoseconds after the hold the data, and at least 10 nanoseconds before the next clock, have the next data ready, that's a contract for the memory to fulfill. Having understood that, let's go back to our question from before. Can we just put a flip-flop on all inputs and a flip-flop on all outputs? Obviously, if we do that, we'll find it very simple to keep up with the promises of the timing diagram, with the contract that the timing diagram imposes. However, we might run into another problem. If we look at this table on page 20 of the datasheet, we see all the addressing modes that the 65C02 supports. For each addressing mode, it tells us how many cycles a command that uses this addressing mode takes. So if we take, for example, the absolute address addressing mode, we see that a command using the absolute address addressing mode needs to take 4 cycles. We have a comment number 3, but comment number 3 merely talks about if it's a read, modify, write. So basically 4 cycles. Is that actually the case? Let's find out. If we go to this table, we have all of the CPU's opcodes. The ones marked in green are ones I've already implemented in my design. As usual, you can find a link to my project in the comments below. And while you're down there, right about here, there's this like button, which really begs for your attention. If we look here, we have AD, load A, absolute. Does this command actually take 4 cycles? The table says it does, but maybe we don't believe the table. This website is called Visual 6502. It's a great website, and what it has a dump of the silicon of the original MOS 6502. Using this site, we can put data in memory, and then simulate how the CPU actually works. And this does by simulating the silicon, the flip-flops, the transistors that are embedded on the original 6502. So we want to know how many cycles the load A absolute command takes. We place AD in the first command here, in the first byte here, and then we need to fill in an address. So let's use 3412, and then put the break command afterwards, just so we notice that we've done. Press the up button and the bus is updated. Load A absolute. First cycle is the fetch. Second cycle fetches from address 1, and that's the least significant byte of the address to fetch. Third cycle fetches the most significant byte. And the next cycle, that's 3 cycles, right? The next cycle fetches from address 1234, which is the address we asked for, and it fetches the value 0. And the next cycle, we already start executing the break command, and we can see that the accumulator actually received the value 0. So yes, this command actually took 4 cycles. Knowing all that, let's draw a timing diagram for our implementation. The first thing we want to draw is the clock. What we'll do is we'll draw the high area of the clock, and we'll draw the low area of the clock. And since the clock edges are really important to us, let's draw them and also carry them on. Next, let's draw the address line. Now, we pretty much already know what value it will have at each clock cycle. So we know it loads the values on the falling edge of the clock and keeps it until the next falling edge of the clock. That's what we see here, right? So some setup time, and then hooked on the falling edge of the clock, the address line becomes valid, and it continues to be valid until a little after the next falling edge. So the address line will start somewhere here, and then will become valid, and we said we'll start with address 400, and then it switches to 401, and then 402, and then we read from the memory address. So 1, 2, 3, 4. And then we have the next instruction at 403. So that's our address bus. Next, let's have a look at our data bus. And we pretty much already know what that has to say too. So we need around the falling edge, we need AD. And then around the falling edge, we need 3, 4. And then around the falling edge, we need 1, 2. And then around the falling edge, we have our value from memory, which said was B2. And the next instruction is a break, so that's 0, 0. So that's our data bus. Next, we would like to figure out what our data latch is supposed to read. So remember, we said that we have a data latch on the input. And the first question we need to ask ourselves is, when can we latch it? It's pretty obvious the answer is on the falling edge of the clock. We cannot latch it anywhere else because only on the falling edge of the clock we're guaranteed to actually have the data from the data bus. So our data latch is supposed to, and to understand what the data latch is used for, it's used to hold the address while we're constructing it, while we're assembling it. So here we read from 401 and we're getting the least significant byte of the address, and that goes into the lower end of the data latch. And here we read from 402 and we're reading the most significant byte. So that goes into the high area of the data latch. And then it can output on the address bus, on both halves of the address bus, the address it has received. And that goes out on the address line as 1, 2, 3, 4 is the address we're looking for. So our DL at the falling edge here will contain XX, here it will not contain anything. So let's mark it as XX. And then on this falling edge, it will switch to XX34. And on this falling edge, it will switch to 1, 2, 3, 4. Which is fine. I mean, it's the same cycle we need to already output 1, 2, 3, 4, but that's fine. The data is here. Except we have another register here. So the next question is, when do we update those two registers? And here again, we go back to the CPU's timing diagram, and we see that the address bus needs to be updated just past the falling edge of the clock, which means that the falling edge of the clock needs to trigger an update to this, which works well for this register, the bus low register, because on the falling edge here, so we have the address bus low and address bus high. So there's no problem making sure that the address bus low at this point switches to 3, 4. It's not a problem. It was available before the clock. However, we also need the address bus high at this point to switch to 1, 2. And that's where we run into a wall. Because here's the thing. In order for this post the falling edge of the clock to receive 1, 2, the 1, 2 needs to be loaded here before the falling edge of the clock. But before the falling edge of the clock, the 1, 2 is not yet available on the data latch. The data latch only has the 1, 2 after the falling edge of the clock, which means that we cannot latch both the input and the output. There's just no way to complete the load A instruction in 4 cycles if that's what we're going to do. Which shows you why timing diagrams are so important. They can teach you not only how to read them and understand the requirements, but also how to apply the requirements to your own design in order to see whether the design lives up to the requirements. And in our case, we've seen that we cannot both latch in the inputs and the outputs and be cycle accurate to the original 6502. But we can do all 3. I hope you found this useful. Feel free to drop a note in the comments if you find anything here unclear or that needs clarification. And thank you for watching.